Process iteration and injection molding has been around for well over a century with the intent of getting the best parts out of the press in the least amount of time. Simulation was developed to make this methodology more efficient by using a virtual molding environment to perform and evaluate the iterations without the need for a molding trial. Today, we'll be exploring the different processing methods available in simulation as well as the plethora of variables at your disposal through Moldex3D's Process Wizard. I'm Alex Baker, and welcome to another Moldex3D Tips and Tricks.
There are various ways that you can define a process in Moldex 3D. I'm going to click on the main button here to create a brand new process. However, you can also create a default process using the Moldex 3D recommendation. The Moldex 3D process wizard has three different setting methods, as we call them. There is CAE mode, machine mode 1, and machine mode 2. CAE mode is going to be used when you don't have the mold in production. The parameterization in CAE mode for the process makes a lot more sense for an engineer that has not yet developed a process for their real mold situation. The machine mode 1 will allow you to set up a real machine. It'll allow you to select the real machine as you can see down here. And the parameterization that you set up for machine mode will be more aligned with the instrumentation on the real molding machine. This setting method will make more sense when correlated to a real molding machine. Machine mode 2 is kind of a combination between machine mode 1 and CAE mode. Machine mode 2 allows you to set up a lot of the constraints based on a real machine with some CAE settings mixed in. Starting off with CAE mode allows us to set up the simulation as though it makes sense in the simulation world. As such, we're not using a real molding machine, we're actually just specifying the maximum pressure limits for that machine, which will allow us to define some of the parameters later on. The maximum injection pressure is going to be the machine's maximum pressure capabilities. I usually set this a little bit higher when I'm in CAE mode. If you hit this maximum pressure accidentally, you can get in a situation where you short shot due to the pressure of the machine not having enough capability. Especially if you're running a simulation for the first time on this part, we might not know how much pressure is needed to mold the part. So having a higher pressure than necessary can allow us to avoid this pressure limited scenario. I use 350 MPa as a general recommendation. The default of 250 MPa will work for most situations as well if you want to keep the default. Going to the next tab, filling and packing, the first parameter that we see up top here is the filling time. I'll just set this to 1 second to make the math a little bit easier. Filling time is not necessarily a constraint on the simulation, but rather a target for the simulation. What this filling time dictates is the initial flow rate of the material through your melt entrance. We already know what the fill volume is going to be, what our injecting volume needs to be. So when we define this filling time as a seconds, that allows the software to calculate the initial flow rate of material into your geometry. Based on how that material flows into your geometry, whether there's shear heating or hesitation or some other flow inhibiting or flow acceleration phenomenon, the output filling time from the simulation might be slightly different than the input. So if I set a filling time of 1 second here, I might expect there to be about 1 second as my output, but it might fluctuate either way. It could be 0.95 seconds, it could be 1.05 seconds. And that's totally normal because this filling time is not necessarily a constraint to the simulation, but rather a target. If you don't know what filling time to use, you can use the following equation. Filling time is equal to the maximum flow length divided by the injection speed in millimeters per second. Now, when I say the maximum injection time, that refers to the distance from the melt entrance to the end of fill, whether it's on this side or on this side. Keep in mind, if my gate were over here, I might need to go over to this corner of my geometry and then to the end of fill in this measurement so that I don't traverse over empty space. We want to get a realistic idea of the maximum flow length of our plastic. The injection speed Most injection processes will have a 100 to 120 millimeters per second injection speed. And so the rule of thumb is going to take whatever your maximum flow length is, divide that by 100, and that will give you a good relative starting point for your filling time. And then based on what happens in that simulation, you can adjust the filling time accordingly. Because this filling time sets the initial flow rate, the flow rate profile really just allows us to modulate that flow rate based on when and how fast the material is going to be injected into the part. By default, we're going to see a set three section numbers in this flow rate profile: 1, 2, and 3. The x-axis is time as a percentage, which we can use the drop down at the top here to change to seconds if you want to. You'll see that the y-axis on this graph is flow rate, but it is as a percentage instead of a cc's per second or an inches cubed per second. The reason for this is because the actual value of the flow rate has been dictated by the filling time already. What we're doing now is creating a ratio of the flow rate based on the different profile sections here. So when we have a 3-section profile like this, we're not saying that this is 30% of whatever value is dictated by the filling time. We're actually putting this into a ratio based on the amount of material to be injected. So let's create a more simple scenario. Let's do a 2-section profile where one side is 100% and the other side is 50%. This flow rate profile, the area under the curve here, represents the amount of material to be injected into my part volume. I can divide this profile based on into 3 equivalent sections if I create a divider right in the middle of this first section here. So what this is saying is that we are going to be injecting 2/3 of our material in the first half of our filling time. The last third of our material is going to be injected in the last half of our filling time. So, as a response, the flow rate is going to be that much higher during the first half than it is during the second half. Again, this flow rate profile does not dictate the actual value of flow rate, it just calculates the ratio of flow rates with respect to the different stages of your profile. To make things simple and much less confusing, I recommend to just use a 1-section profile, and you can make the flow rate at 100%, and that will make it so that there is the same flow rate throughout the entire process. This is typically what most processes will use anyways, and there will be some sort of transition up to this maximum flow rate, and then a transition once we get to the VP switch. The injection pressure profile is meant to be a further limit on the maximum injection pressure that we set back in the project settings tab. You can see here the maximum pressure is 350 MPa, and we can actually change this drop down at the top to be, instead of as a percentage of this 350 MPa, we can actually just choose to specify this directly. In most real processes, your machine will have a certain capability. That doesn't necessarily mean that you want to be using that entire capability during your injection process. So this profile allows us to set a safety factor on the machine's capabilities. In CAE mode, however, we usually don't have a process developed yet, and so there's not really a need to be reducing this maximum value. The more times than not, I will be setting this injection pressure profile to be 100% when using CAE mode. The VP switchover is where we are going to be transitioning it from the velocity control stage to the pressure control stage. That's what VP stands for, is velocity to pressure. If we were to switch over just as the material becomes 100% filled, unfortunately, that's going to create a very large pressure gradient onto your machine, which will create a very large impulsive force, which can actually damage your machine. You can almost think of this VP switch like stopping at a stop sign. If you wait until you get to the stop sign to try to stop, the momentum of your car will have to slow down very quickly, shifting everything in the car very quickly. If we ease into the pressure control stage from the velocity control stage, there's much less of an impulsive force, and we're able to get a nice, smooth transition without injuring the machine. And so typically for most injection molding processes, you will be using some sort of switchover before 100%. The default in Moldex3D will use 98% of the volume percent filled. So once 98% of the runner plus part volume has been filled, we switch over from the constant velocity stage or constant flow rate to a constant pressure condition during the packing stage. The VP switchover is going to be your transition point. If we switch over too late, as I mentioned, there's going to be a large impulsive force, which usually requires a higher amount of pressure in order to fill your part geometry. But on the other side, if I switch over too early, let's say at around 90%, when I go from my constant flow rate to my constant pressure, we're no longer pushing new material into the geometry with a flow rate. We're rather using a constant holding pressure. And therefore, the only way for material to move forward is by the already existing momentum of the material. So in most situations, that material's momentum is not enough to allow that material to get all the way to the end of fill, and therefore you get a short shot as a result. So if we switch over too early, we can end up getting a short shot in our process. If we switch over too late, we can end up hurting our machine. So we need to find some point in the middle of those. 98% is a very safe value, but most processes will use somewhere in the realm of 95 to 98%. The last option here allows you to set your VP switchover as a control point pressure. So let's say the pressure at this particular location in my geometry needs to be, let's say 50 MPa so that we can switch over to our packing stage. A more common scenario is if we set our VP switchover close to the end of fill, and then now we can set this as our control point. If I just set maybe zero point 0.1 MPa, we'll say that now, once the melt front reaches this point pretty much, 0.1 MPa being a very small pressure number, once the melt front reaches this point, we're going to be switching over to our packing stage. So this almost gives a location-based VP switchover option rather than a volume percent filled switchover option. If you're setting up your simulation for the first time, I recommend you to use the default, which will be volume percent filled and 98%, which is the default. The next parameter we're going to talk about here is the packing time. The packing time is going to dictate the amount of time that this constant pressure is going to be applied. During the filling stage, we're applying a constant flow rate or a constant velocity. During the packing stage, we're going to be applying a constant pressure. And this amount of time is going to dictate how long that pressure is going to be applied. In the injection molding process, I always recommend to set this packing time initially. If I'm running an initial simulation, I'll set this packing time a lot longer than needed to be sure that I can see all of the packing effects needed. And then I can go back and modulate that packing time to align with when the packing effect really stops. Ultimately, the purpose of the packing stage is to be able to compress material into our part geometry to reduce the effects of material shrinkage. We're trying to combat that shrinkage by just increasing the density of the material, but there is going to be a point where either the material freezes and you're not able to push material into the geometry any longer, or there's so much compression effect that has occurred where there's no longer the ability to push more material into your geometry. And that point is where the packing time should stop. Once we're not pushing material into the geometry anymore, we're in the cooling stage effectively, and we can shift the remaining time from the packing stage into the cooling stage. Maybe that allows us to optimize our cycle time a little bit better. Generally speaking, when I set up a packing time for a preliminary simulation, I'll set the packing time at 10 times the filling time. This will usually be quite a bit longer than needed, but again, this ensures that we have enough time to be able to study the packing effects that are going on. If we set the packing time too short, then we don't actually know how much packing time we'll need, and it might require multiple simulations to figure out when that is. Versus if I set the packing time longer than necessary, I can guarantee that I'm going to know how much packing time I need for my next simulation. Then I can go in, adjust my packing time to whatever value is needed, and it's just a 2 simulation process versus a 3+ simulation process. So that defines how long we are going to be holding this pressure, but what pressure are we actually holding? That's what the next two fields here allow us to dictate. The drop down here allows us to decide between one of two options. We can either apply our packing pressure as it refers to our end of filling pressure or at the VP switch point, or we can set the packing pressure directly by using machine pressure. The default is going to be packing pressure refers to end of filling pressure. And when I go into my packing pressure profile, we'll see that it is going to apply a 3-section profile by default. I usually like to take this down to one section, especially for a preliminary simulation such as this one, to reduce the amount of variability that we experience in the simulation. If you click on the dropdown at the top, you'll actually see that there's no way to set the packing pressure as an MPa or a PSI. And the reason for that is this packing pressure is going to be a reference to the end of filling pressure or the VP switch pressure. Whatever pressure is happening at that VP switch moment, at that 98% as we have it set in this simulation, we're going to be taking a percentage of that to be our packing pressure. So let's say I have 10,000 psi as my end of filling pressure, and I set 70% as my packing pressure. That means that my packing pressure setting is going to be 7,000 psi. This setting will guarantee that we have some sort of reasonable packing pressure throughout our process. Packing pressure refers to machine pressure, allows you to set this pressure directly. If I click on the drop down at the top, you'll be able to see that the packing pressure is able to be applied as an MPa if you're in metric units or PSI if you're in English units. The maximum pressure that we're able to apply here was defined back in the first tab when we defined the maximum packing pressure, which is effectively the machine's capabilities. This option should only be used if you have a process available to you already, because if I set, for example, 100 MPa as my packing pressure, but I only get to 50 MPa in my injection stage, instead of transitioning downwards from my filling stage to my packing stage, which is typically what you want to do, I'm going to be transitioning upwards. So instead of decelerating the flow, I'm actually going to be accelerating the flow, and that can actually end up hurting my machine in the long run. I'll end up packing at a very high pressure with respect to the amount of pressure required to fill the part, which means I can get a very high pressure right at the gate region, and that can cause overpacking as well. So typically, when I'm setting up a preliminary simulation, I'll be using the end of filling pressure reference, and I'll use a 70% profile. This will guarantee that I have some sort of reasonable setting going into my preliminary simulation, and then we can adjust that profile wherever needed. The last two values here allow us to set up the temperature of the material and the mold respectively. The melt temperature is going to be the temperature of the melt coming out of the melt entrance, and the default here is actually set by your material profile. Material profile also dictates a soft constraint for this temperature range. You'll see that here if I try to go too far outside of the recommendation. Typically it's plus or minus 20 degrees. If we go too far outside of this recommended range, we can start extrapolating the material data, and not all of the material properties are going to be valid when doing a linear interpolation like that. So it is very highly recommended to stay within this range for the melt temperature to make sure that your simulation is as valid as possible. Especially if you're running a preliminary simulation, you can just use the defaults, and then you can start modulating your melt temperature as needed. The mold temperature, on the other hand, is still soft constrained to a range, but it is less necessary to stay within that range for the mold temperature because this is just the initial condition into the cooling stage. At the beginning of the cooling stage, your entire mold will be at this temperature, and the steady state calculation will determine what the temperature distribution is going to be going into the rest of the process. When setting up a preliminary simulation, I recommend to just use the default, but this value is less necessary to stay at the default than the melt temperature. That wraps things up for CAE mode. Let's now jump into machine mode to see how we can set up the process as it applies to a real molding machine. In CAE mode, we set up a lot of the process parameters as it makes sense in the simulation world, but machine mode 1 will allow us to set up our parameters as it makes sense to a real molding machine. which is actually what we're going to be defining down at the bottom of this project settings tab. You can click on view to view the default machine that it has applied for you, see all of the default constraints and the default characteristics of this machine at a glance. More than likely, however, we're going to be wanting to change this machine to be more aligned with what we're actually using in the process. To do so, you can click on the dropdown and hit New to open up the machine database. The machines are organized by their manufacturer and then by the grade name of that machine. You will see that there are two icons next to the manufacturers. There's one that looks like an M and one that looks like an injection unit. A manufacturer with an M next to them means that we have worked with that manufacturer specifically to incorporate their machine interface into our process wizard. I'm going to use a machine from a manufacturer that has the M. I'm just going to use the first Arberg machine here to show off that machine interface a little bit later on. Over on the right side here, where the machine parameters actually show up, we have 6 main parameters that we're going to be defining for this machine. And these are typically the only parameters that I mess around with if I need to. If I don't see the machine that I'm actually using in this list, you can actually go in and customize that machine to your capabilities. So let's say I have a 1200 ton, 1300, 150, but a 40 millimeter screw. Then I can go in and say, okay, well, most of the parameters are pretty much the same for this particular machine grade. I just need a larger screw. So I can go in and change this machine. I can actually edit these machine profiles. And now this is actually going to be located in my user bank up at the top. You're not actually editing the machine database list here. You're actually going to be creating your own customized machine that you can use later on as well. This screw diameter, in my case here, I would just change this to 40, which is the diameter of the screw head. Your screw stroke, actually, the rest of these parameters are really going to be kind of the capabilities of the machine. The screw stroke is the maximum screw stroke available. So this is not necessarily defining a process parameter, but rather just the maximum capabilities of this machine specifically. The maximum shot weight is the amount of material that can be injected. Maximum injection pressure is the highest amount of pressure that can be applied by either our hydraulic system or the electronic system. Maximum injection rate is the highest speed that we can apply to the screw. And then clamping force is the maximum amount of force applied by our clamping system. Once we're satisfied with these parameters, that's pretty much it as far as the customization of this machine goes. We have some other parameters here that are certainly applicable to other types of simulations, but for a traditional injection molding simulation, these 6 parameters are the only ones that really come into play. So once you're satisfied with this machine, you can press OK, and that will bring you back into the process wizard. Whenever you change your machine, it's going to ask you if you want to scale your profile settings. And typically, I'll say yes so that I can keep all of the process settings that I might have already applied. Now, if I select a machine that has an M next to it, so remember the manufacturer for Arberg had that M icon, then this machine interface checkbox will appear down at the bottom. And now when I hit next, you'll actually see that the machine interface pops up where we can actually start to interact with this machine interface and edit these values, which will be directly translated into the process wizard. Now note that only the icons that are necessary for inputs into Moldex3D will be available, but this interface is very interactable. You'll be able to set up your parameters as it makes sense on the real molding machine. If you're not familiar with that interface, but you know what machine you want to be using, then you can elect to not use the machine interface and set everything up instead in the process wizard. And when we're specifying the process in machine mode 1, you'll notice that the parameters will look a lot more similar to what you would be inputting into your real process condition for your production cycle. The first thing that you'll probably notice is that there is no longer a filling time, but rather that is replaced by a stroke time that you cannot edit. And the reason for that is in machine mode 1, instead of dictating the flow rate using the filling time, we're going to be dictating the flow rate directly, and that flow rate that we input will dictate the stroke time here. So it's kind of the opposite way around. All right, so as such, I'm going to go into the flow rate profile, you'll see that the injection velocity by default is as a percentage, but this time instead of as a ratio, like we saw in CAE mode, this is actually a percentage of the maximum flow rate capabilities of our machine. You can change this dropdown at the top to use either a linear velocity as a millimeters per second or as a volumetric flow rate, and you can set that directly here. There's not any recommendations for a generic process using machine mode because whenever you're using machine mode, you should already have the process defined. If you don't have a process defined and you are using Moldex3D, it's very highly recommended to use CAE mode instead as a means to get you a more consistently viable process. All right, so I can update my injection velocity here. We'll see that when I change my injection velocity, my stroke time will change inversely. So if I go to 50 millimeters per second, whereas the default was 62, I'm going to be injecting slower, which means that my stroke time should increase. And also, I can change my RAM position. By default, it will use the maximum of allowable RAM position or the maximum stroke size that we set in our machine profile. If I change this RAM position, it's going to alter the amount of material, the injecting volume, accordingly. Now, there are two warnings that are possible to see here. The first of which is if you set the volume lower than your part volume. So this process wizard is already indicating to me I need to have an initial RAM position greater than 136 millimeters so that I can actually fill out my part. If I inject too little material, the machine screw will get down to 0 before the part is filled, and therefore I get a short shot. Alternatively, in this situation specifically, the maximum stroke of my machine is actually 110 millimeters, which means I can't actually get up to that 136 millimeter recommendation that it was giving me. So in this case, I actually do have too small of a machine to inject this part. So in that case, I might want to go back and select a larger machine. So that's all just to show that this process wizard is smart enough to recognize when there is a problem in the process condition input. The injection pressure profile will usually be using some sort of safety constraint or safety factor to prohibit us from using the entirety of our machine's capabilities. 70% is a pretty good safety factor, but it will vary from machine to machine. You can look at your manufacturer's specification to know how much pressure you should be exerting in your process. The VP switchover, for the most part, has the same capabilities as what we saw in CAE mode. You can do by volume percent filled, excluding the runner, control point pressure, and injection pressure. But there is a fifth option that is actually the default here, and it is by RAM position. Back in CAE mode, we talked about switching over using a control point on our geometry, but this by RAM position is going to track how far the RAM has traversed in our total stroke. So in this case, I had a total stroke of 90 millimeters. So it's saying here, if I set this to 2 millimeters, let's say, once we have traversed 88 millimeters of that total stroke, then we're going to switch over to the pressure stage. All right, so this is a control for your switchover based on your RAM position rather than by a percent filled or by a control point location, and will be more correlatable to a real process. Most of the time, a real molding process will have a switchover specification by RAM position rather than as a percent filled. The packing setting works very similarly to what we saw back in CAE mode. Just instead of having the end of filling pressure reference, now we only have a machine pressure reference. You can only set your pressure directly as an MPa or a PSI or as a percentage of your machine's capabilities. You can see here the maximum capability of the machine is 162 MPa. And then we can set our packing pressure accordingly as a direct input. Melt temperature and mold temperature both are recommended from the material file once again, and you can go in that soft constraint that we discussed in CAE mode, still applies. The third setting method here is machine mode 2, and you can see in parentheses it says by injection time, whereas in machine mode 1 it says by profile. We'll see that we no longer have access to that machine interface down here at the bottom, and when we hit next, the first thing you'll probably see is that the stroke time, which was not editable back in machine mode 1, has been switched to injection time. You'll notice a big empty space down here where packing time used to be. When we're using machine mode 2, the injection time is going to be your filling time plus your packing time. And then your flow rate is going to dictate how fast the material is going to get into your part geometry. The remainder of this time is going to be your pack and hold. So if I set a 10-second injection time and it only takes 2 seconds to fill my part geometry, the rest of that 8 seconds is going to be pack and hold. The rest of the parameterization here works pretty similarly, with the exception that you are able to set by end of filling pressure in this particular version of machine mode. As I mentioned at the beginning, the machine mode 2 option is more of a combination of CAE mode and machine mode 1, and there's not really a reason to be combining the two. It is very rare to be setting your injection time as a way to define your process. Usually, you want to be a little bit more specific for how long you should be injecting during the filling stage and how long you should be injecting during the packing stage. Just to recap, between CAE mode, machine mode 1, and machine mode 2, CAE mode is typically going to be used when you don't yet have a process specified, or if the mold is not in production. Machine mode 1 will be used when you have the machine in production and you have a process developed. It will allow you to translate that information more smoothly. And machine mode 2 is very niche use and as a combination between CAE mode and machine mode 1. So now I would like to talk about cooling. The cooling parameters are the same between each of the three setting methods. And I'll just go top to bottom here to describe each of the different settings that we have here in the cooling tab. The cooling method allows us to either have a constant cooling channel temperature or a varying cooling channel temperature. If I want a constant cooling channel temperature, I'll use general. And if I want to vary the cooling channel temperature throughout my process, like a variotherm process or an RHCM, rapid heating, rapid cooling, I can use transient. Initial mold temperature will come as a default from the mold temperature in the filling and packing settings, and there's not a need to change this. In most processes, that will be grayed out. The air temperature is going to be the ambient temperature around our mold and is also going to be the temperature that is in contact with our mold during the mold open stage of our process. This eject temperature dictates when the material is cooled down enough to where the part is ejectable. This is going to be different from the freeze temperature of the material, where the material initially transitions from the molten stage to the solidified stage. The eject temperature dictates where that material is solid enough to be able to eject. The cooling time is the amount of time that the material is in the mold after the packing stage. If I'm setting up a preliminary simulation, I'll typically set this cooling time as 2 times the packing time, just to make sure, once again, that I have enough cooling time to be able to evaluate the different effects that I want to be able to see. Kind of like what we talked about with the packing time. The mold open time is the amount of time that the mold is going to be exposed to that ambient temperature, and you should use a time here that would more closely correlate with other processes that would be similar to this one. If it's an automated process, then you might be able to use a smaller mold open time. If it's more of a manual unloading process, then it might be a little bit longer. Ejection timing after mold open allows you to open up the mold, exposing it to ambient air before ejecting the part. So one half of the mold is going to still be in contact with the part geometry before the part is ejected. Mold preheat is a way for you to set a preheating simulation for thermoset materials. If I have a heating system in my mold rather than a cooling system, then this mold preheat will allow me to run sort of a steady state condition like what we do in our cooling stage, but for heating instead. And there is a specific analysis type that we can use to run this mold preheat, as we can see right here. The cooling and heating button down at the bottom allows you to set up your cooling channel temperatures. These temperatures can be independent of one another. We can see in this situation, I have 4 different cooling channels. And if 2 of these are on the core side, 2 of these are on the cavity side, I can actually set them as different temperatures from one another. I can either dictate the flow rate of the coolant going through these channels, or if I use the drop down at the top here, I can specify the pressure of the coolant going through these channels. We have water, oil, steam, air, and liquid nitrogen as options for you to select. And then the other 2 options over here on the right side are the diameters of the cooling channels, which you cannot edit. And then the Reynolds number is calculated from the channel diameter, the type of coolant, and the flow rate of the material going through that channel. The next available tab here for mold metal material allows us to specify what the mold metal is around our geometry, keeping in mind that this will only be available if you assign some sort of cooling system. If you don't, then this option will not be available. You can see that we have a quite extensive list of mold metals. The default will always be P20, but you can see a lot of common metals here like QC10, Mold Max, aluminum, 420 stainless, H13, S7. There's a lot of very common materials under here that you have at your disposal. And if you have set up inserts in your simulation, those will also show up in this list as separate line items where you'll be able to specify the material differently from the main mold metal. The next row of buttons allows you to set up the initial temperature of either your mold inserts or your part inserts. If you have those attributions in your simulations, you'll be able to set kind of a preheated insert scenario. By default, they will assume the input mold temperature. Eject criteria does not come up very often, but it does allow you to set up when the part should theoretically be ejected from the mold. And then the estimate cooling time over here is a very basic heat transfer calculation. It will estimate your cooling time based on your average part thickness, among other heat transfer parameters. If you hit next here at the bottom, it will bring you to the summary tab. And if you scroll down, you'll see the cycle time. The cycle time will be an addition between the filling time, packing time, cooling time, and mold open time for CAE mode, and the stroke time plus packing time plus cooling time plus mold open time for machine mode. And this is just a way for you to confirm that your process that you've input into Moldex3D aligns with the real process that you might be wanting to replicate.
If you like this video, you can subscribe to the channel to receive notifications on when new videos are posted. And if you have a suggestion for a future video topic, you can leave that in the comment section below. Thanks for watching, and we'll see you in the next Moldex 3D tips and tricks.